Well, we're going to continue to look at hypothesis testing. And now we want to kind of focus this lesson on what the evidence is for our p-value, which is that probability that it would happen for that given test. Now, if you've not done so, make sure you watch this YouTube video first, which the link for it is in your notes. Then go ahead and continue this video. So, as we talk about Paul, he correctly predicted 8 World Cup games in a row. Oh, so is this evidence that Paul's guessing correctly is greater than 50%? As in, does he somehow know something that we don't to be able to figure out who's going to win? So what would be the null hypothesis and the alternative hypothesis? Well, the null hypothesis would be the probability is 1/2. I mean, you either win the game or you lose the game, and assuming all things are equal, it's a 50-50 chance. So we're wondering if this probability with Paul is really greater than 50% or zero 0.5. So how unusual is it to see that our sample statistic is as extreme as what we observed with Paul, as in if this is true? That's kind of the key question here. So if it is very unusual to get these results, we would say it's statistically significant and we have evidence against our null hypothesis. So how do we measure how unusual this sample statistic is, assuming your null hypothesis is true? Well, to do that, we want to go ahead and see what our statistic would be like compared to what we would be expecting if our null hypothesis were true. So thinking back to Paul the Octopus, we know the kinds of statistics we would observe if it was by random chance, assuming it was a 50-50 chance. But how would you figure that out? Well, one of the ways to do this, just a second here, would be with coins or something along that lines. But we had a sample size of 8 because it was 8 games you correctly predicted. So to simulate this, you could take a coin. You could flip that coin 8 times and record the results. You could let heads be correct, tails be incorrect, and so on. And then you could figure out your proportion of heads after you flip the coin 8 times. That would be your sample proportion. Now, how extreme is it to get a proportion of 1, as in get 8 heads in a row? Well, the results we would get by flipping the coin 8 times, getting our proportion of heads, recording that, flipping the coin 8 more times, getting that proportion of heads, and so on. If we started plotting all those different results, we would get our randomization distribution. And it shows basically the random occurrences that should be or could be occurring if your null hypothesis is true. So you do lots of simulations. Typically, we're going to use technology to do that, and more specifically, StatKey. And I'll be modeling StatKey here in a different video. So here, with our null hypothesis being true and a sample size being 8, and here we did 200 simulations, 200 samples of size 8. This is what the distribution looked like using StatKey. Now, how unusual is it to see a sample statistic as extreme as we did, assuming your null hypothesis is true? That's the key thing that we're going to look at. That ends up being our p-value. Our p-value is the chance of getting our sample statistic as extreme or more extreme than what we observed. assuming your null hypothesis is true. And you might be wondering, what all does that mean? Well, when we start looking at stat key on another slide here, I think it'll start to make more sense. So just be patient with yourself. So what would be the p-value of getting 8 out of 8 correct for our Paul the Octopus? Well, that's getting a sample statistic of a 1, as in 100% for 8 out of 8. When we look back at our random sampling distribution, here's our null hypothesis right here, 0.5. And we want to get over here to 1. And that's occurring only a couple of times here. And so our p-value is this 0.004, which means if our null hypothesis is 0.5, what are the chances of getting 8 out of 8 heads? Well, the chances of that occurring is 0.004 or 0.4%, assuming that this is true. Now, since that's really, really small, it's not likely that this is correct. And so that's what we're going to be getting into. So that's our sample statistic down here of 1. And this is the probability of getting that statistic or more extreme. So what kind of statistics would we get out of a random chance? Assuming it's true, that's our randomization distribution. Getting something as extreme or more extreme than our sample statistic is our p-value. Typically, when you're looking at stat key or a bell-shaped curve, it's going to be what's in one of the tails or the other tail or both tails. So let's consider this one here where we're looking at the death penalty. So read through this. And we want to find favor to see if we want to find if the death penalty, those who are in favor, decreased from 1980 to 2010. So we first of all need to look at our hypotheses. So we're going to have our proportion that are in favor of the death penalty for 1980 and a P with a subscript 2010 for the 2010 year. Once again, your null hypothesis is always an equal sign. And we want to find evidence if it decreased so that we would be expecting the 2010 to be less than the 1980, or the 1980 to be greater than. So if you read it from left to right, the 1980 proportion is greater than the proportion for the 2010. Now, if you wanted, you could have subtracted the proportion of 2010 from both sides, so it'd be proportion to 1980 minus proportion of 2010 equal to 0. Same idea down here. It does not make a difference. So if you go ahead and take 663 divided by the total here, which is 1,005, we get this. For 2010, you take 640 divided by the total here, which is 1,000, we get this. We want to go ahead and subtract those two, and we get this. That's our, for the most part, our sample statistic that we're going to test. So how extreme is it to get a sample statistic of a 0.02, assuming that they are equal? That's where we use stat key, and I'll model that here in a bit for you live. So we're doing the difference in two proportions, and we're doing a test. We need to go ahead and edit our data and enter in the data, and that's what we have right here. Our proportions are here, subtracting them is here. We had a 0.02 for our results, our sample statistic. So what's that? And to the right, that's what's here in red. The probability of that occurring is our p-value, and that is 0.164. So the proportion supporting the death penalty has not changed because this is not a real small p-value. As in, we did not necessarily find evidence to support that there was a change. So here we have our null hypothesis being 0. We're wondering about what's greater than 0. So here's 0 here. We're wondering about being greater than. So if our sample statistic was 0.1, that would be here. Being greater than that would be going from straight up and down and to the right. So this whole fairly large tail here. If it was 0.3 for R, well, 0.3 would be here. That would be going straight up and down and to the right. Definitely less, not as much there. Or 0.5. So here's 0.5 going straight up and just to the right. Well, you can see that there's just 6 dots there, which is really not much comparatively. So if you have, looking at your p-values, we're really concerned about what's at that sample statistic, and because it's greater than, and to the right of that. If it was a less than, you'd be at that sample statistic and going to the left. But it's greater than. So 0.1 here, that's a fairly large chunk. So which p-value would that be? That would be this one here. When we looked at 0.5 here, that was here, and just a couple of things over here, that's got to be our really small p-value here. And the 0.3 one would have to be in the middle with the 0.15. Your alternative hypotheses are always greater than or less than for one-sided. But if it's just looking for different, or you don't necessarily know greater than or less than, then it's a two-sided, which is a not equal to. Your proportion, your p-value is the proportion of the area or dots in the tails, in the direction of which one you're looking at. For greater than, it would be what's to the right of your statistic and above, or less than what's below and above, or for your two-sided, it's what's in both tails. So if your null hypothesis is 0 and you're wondering what's greater than, and you had a 2 for your sample statistic, you go to 2, and because it's greater than, you'd be at 2, and what's to the right of 2? And that would be to the right. And that's your right tail when you're dealing with greater than. If it's a less than, and then it's left tail. Less than, left, both begin with L. So if we had a sample statistic being -1, here we'd be at -1, and we'd want to be going to the left because it's less than, and then that would be your p-value right there. If it was a not equal to, then you got to look at both tails. So you got to look at what's 2 and what's at -2. So here's 2 and to the right, here's approximately -2 and to the left. So you got to look at both tails for a not equal to. So let's go back to the sleep and caffeine. So these are the null and alternative hypotheses. If we two-tail because of the not equal to. So let's find our p-value. Looking at stat key, running it, we would get this here. Two-tail, we had 3, so you go to 3, and it's the area that's over here, which is 0.022, and the area that's over here, 0.022. So that's a total area of 0.044. Now, which one of these would give you evidence to support your alternative? So once again, same as a couple slides ago, which one would give you evidence to support your alternative? That would be the one with the smallest p-value. That would be the one that was 0.5 way over here because you only had a few small dots. And that would be your p-value, 0.005.